Hello everyone, and welcome back to some more remote learning. In today's example video, we're going to dive into the derivatives of inverse functions. But first, let's find the derivative of just our function f of x equals x cubed, and we're going to find that derivative at the point 2, 8. And you can see that when we plug 2 in for x, we do indeed 2 cubed gives us 8. So we do indeed get that value of 8. So finding the derivative of f of x, f prime of x, that's going to be the derivative of x cubed is 3x squared. So if I want to find the derivative at my point 2, 8, I plug in my x value of 2 and get 3 times 2 squared, 3 times 4, which is 12. So my derivative at my point 2, 8 is 12. Now we're going to find the inverse of this function, and we're going to find the derivative at the point, no longer at the point 2, 8, but now at the point 8, 2. Because remember, an inverse function, how that's related to the original function is it's a reflection over the line x equals y or y equals x. So because we're reflecting over that line, the x and y point values will get switched. So what was previously x naught, y naught is now going to be y naught, x naught. So let's go ahead and find the inverse of that function. Remembering how to find the inverse of the function, it might be easier to think of this as y equals x cubed and then swap x and y. So as opposed to having f of x equals x cubed, I'm going to write my function as y equals x cubed, but I'm going to switch out y and x. So I'm going to have that x equals y cubed, and then our next step to find that inverse function is to solve for y. So in order to solve for y, I simply take the cube root of x. Taking the cube root of y cubed will leave me with y, so y is going to be equivalent to the cube root of x. Writing this in function notation, the inverse function of x is equal to the cube root of x. Now, my instructions were to find the derivative at the point 8, 2. So how am I going to do that? I'm going to take my derivative with respect to x. So my inverse function's derivative at x is going to be, thinking of this as x to the 1/3, that will be 1/3 times x to the, decrease that exponent by 1, so that's x to the negative 2/3, which I will write as 1 over 3x to the positive 2/3. Now I'm finding its derivative at the point 8, 2, so I'm no longer plugging in 2 like I did up above, I'm plugging in my value of 8, because 8 is now my x value for my function, which was my previous y value. So plugging in 8, I'm going to find the derivative of my inverse function at the point 8. And that's going to be 1 over 3 times 8 to the 2/3. And 8 to the 2/3, the cube root of 8 is 2. 2 squared is 4. This is going to be 1 over 3 times 4, or 1 over 12. Which is pretty similar to what we had up above. It's just 1 over that. So let's go to our formula box and fill this in. Now there's a few things that we're going to need in order to be able to take the derivative of the inverse function. And that's going to be that our function is differentiable and our derivative at our new point in question was not equal to 0. Because, let's look at this formula. We can say the inverse derivative of, well, the point value we plugged in was 8, and that was our original y naught. So the inverse function derivative of y naught at y naught is going to be equal to 1 over f prime of x naught. And that's where y naught is equal to f of x naught. So you can see f of x naught, that f of 2 gave us 8, so our y naught is 8. So when we took the inverse function's derivative, we found the derivative by plugging in 8, not our original 2. However, we could have skipped over and not even found the inverse and then found the derivative at all. We could have completely skipped over this step knowing this relationship, because we know what f prime of x naught is. F prime of x naught is 12, and the inverse function's derivative that we're curious about is at 8. So because 8 is that y naught value, well, the inverse function's derivative at 8 is 1 over f prime of 2, 1 over 12. So if we had this formula first, we would have been able to just plug in those calculated values. However, I think it's important to understand the process. That's why we found the inverse and then found the derivative of the inverse and then found it at the desired point to show that relationship. And again, in order for this to hold true, f of x has to be differentiable, and our f prime of x, what do we not want in our denominator? We don't want that to be 0. So if our derivative at 2 was equal to 0 and not 12, then we would not have been able to figure out the derivative of the inverse function at that y naught value. So using this formula, let's solve example 1. Example 1 says, suppose some function f of x has a derivative value of 2/3 at the point 0,2, a derivative value of 1/2 at the point 2,4, and a derivative value of 5 at the point 4,3. Using this given information, we're going to evaluate the following. And those should be finding the derivative, so I'll adjust that when I go to post the worksheet, but we're going to be finding the derivative of our inverse function at 2 and the derivative of our inverse function at 4. But I think this information is kind of hard to read through, so I'm going to simplify it and write it all down below. So our given information, I'll write in green. The point 0,2 has a derivative value of 2/3. So at 0,2, I know that f prime of 0 is equal to 2/3. And the other given information, at the point 2,4, we have a derivative value of 1,2. So again, 2,4, that means that f prime of 2 is going to be equal to 1/2. And then finally, at the point 4,3, so our point 4,3, we have a derivative value of 5. So f prime of 4 is equal to 5. So here we have our x naught, y naught, and x naught, y naught. And we also have all of our f prime of x naughts included. So if we're trying to find the inverse derivatives function at 2, I need to look at where my y value is 2, and then that's going to be equal to 1 over the function's derivative at x naught. So where does my y value equal 2? That's at this first point here. So this is going to be equivalent to 1 over f prime of x naught, f prime of 0. Because my y value is 2, that's 1 over f prime of 0, and that's going to be 1 over 2/3, which is going to give me 3/2. Now for part B, again, we're looking for when our y value is 4. Because when our y value is 4 in our original function, that's going to be the new input in our inverse function. Because those points get reflected over the y equals x line, so what was once previous y is now our new x value. So I'm going to look for when I had a y value of 4, which occurs here. There's my y value of 4, so that's going to be equal to 1 over f prime of 2. So I'm going to write 1 over f prime of 2, which f prime of 2 is 1/2, so I have 1 over 1/2, which is going to give me a positive 2. So the derivative of my inverse function at 4 is 2. So you can see I have a little bit of extraneous information here, but I could have asked for the inverse function's derivative at 3. So we would have found f prime of 4, which gave us this. But what happens if I would have asked for the inverse function's derivative at, let's not say 4, let's say something along the lines of 0. Because my given information does not contain a y value of 0, we would not be able to solve for that derivative. Or think about this. If f prime of 2 was not equal to 1/2, what if it was equal to 0? Then our derivative for our inverse function would be undefined. We wouldn't be able to calculate it because we can't divide by a 0. So these are just important things to remember as figuring out the derivatives of these inverse functions. So in example 2, as opposed to using a bunch of given information, I'm going to give you a function and a point, and I want you to find the derivative of the inverse function at that given point. And the point that's given is the point on our original function. So remember, we're going to find the derivative of that y value from our original function because we're reflecting over that y equals x line to get our inverse. So zooming into part A, what I want to find is the inverse derivative of y0. What is that equal to? That's going to be 1 over f prime of x0, which x0 in this case is 1. So I'm going to find the derivative of my original function at 1, and I'm going to know what my inverse function's derivative is at that y0 value. So let's calculate that derivative. The derivative of y dy dx is going to be equal to 3x squared plus 2. Derivative of x cubed is 3x squared, derivative of 2x is 2, and I'm going to plug in 1. When I plug in 1, I'm going to get 3 times 1 squared, which is 3, plus 2, which gives me 5. So I know that my derivative dy dx at x equals 1 is going to be a positive 5. So the derivative of my inverse function at y0 is 1 over 5. There we go. But I actually want to know what y0 is, so let's solve for that. When we plug 1 into our original function, 1 cubed plus 2 times 1 is 1 plus 2, which gives us 3 for y. So we found the inverse function's derivative at 3, because our point x0, y0 was 1, 3. Let's move on to part B. In part B, we're trying to find the derivative of our inverse function for that y0 value, or f of 0. So what I'm going to do first is I'm going to find the exact point x0, y0. We know that x0, y0 is 0, f of 0. But what really is that? x0, y0 is 0, if I plug in 0 for x, e to the 4 times 0 is e to the 0, which gives me 1. So I'm going to find the inverse function's derivative at 1. And that's going to be equal to 1 over f prime of x0, 1 over f prime of 0. So let's go ahead and calculate that derivative and then plug 0 in. F prime of x, calculating my derivative, remembering my chain rule, is going to be e to the 4x times 4. And remember, I'm plugging 0 in for x, so f prime of 0 is going to be e to the 0 times 4, which gives me 1 times 4, which is a positive 4. So my derivative in this case, f prime of 0 gave me 4, so my inverse derivative at 1 is 1 over 4. And just to kind of give you a visual image to help you see this, if I have, here's my x, y coordinate system, so I'm going to draw my original function, f of x equals e to the 4x, and I'm going to plot my point 0, 1. So here is roughly e to the 4x, and here's my point 0, 1. So my tangent line for that, f prime of x, has a slope of 4, which you can hopefully envision. Now remember, our function's inverse is reflected over that y equals x line. So if I draw my y equals x line and reflect that function over, now I'm going to plot this at the point 1, 0, because when I reflect it over that y equals x axis, my x and y values switch, So it goes from being the point 0, 1 to now the point 1, 0. And at that point, my tangent line slope is about 1/4. So you can see that's just kind of a rough sketch. I recommend graphing this using some graphing calculator and seeing what it looks like. Being able to see those reflections, understanding that the x and y coordinates will get switched, and understanding how the inverse function's derivative, that slope at y0, is 1 over f prime of x0. But for now, continuing on to part C, we have x squared minus 4x plus 7, and I want to find the derivative of my inverse function of f of negative 2. But what is f of negative 2? Let's solve. If I were to plug negative 2 in for f of x, then I'm going to have negative 2 squared minus 4 times negative 2 plus 7. Negative 2 squared is going to be a positive 4, but I'm subtracting a negative 8, so that's going to be plus 8, and then I'm also adding 7. 8 plus 7 is 15, plus 4, that's going to give me a positive 19. So my point, x0, y0, is really negative 2, 19. So I'm going to find the derivative of my inverse function at 19, which is going to be equal to 1 over f prime of x0, 1 over f prime of negative 2. So let's find that derivative and plug negative 2 right on it. F prime of x is equal to 2x minus 4, so f prime of negative 2 is equal to 2 times negative 2 minus 4, which is going to be negative 4 minus 4, which is a negative 8. So the derivative of my inverse function when y0 is 19 is going to be 1 over negative 8, or simply just negative 1/8. And let's move on to part D. In part D, I'm trying to find the inverse function's derivative at f of 3. So 3 comma f of 3, what is this f of 3? If this is my x0, y0, what is y0? Well, we have to plug 3 right on in. Plugging 3 in, f of 3 is going to give me 3 squared plus 4 times 3 minus 5 all over 3 plus 5. Now this actually might be easier if I simplified my function down before I even started the problem, because f of x can be factored in the numerator. What multiplies to give me a negative 5 and adds to give me a positive 4? That's going to be 5 and negative 1. So I'm going to have x plus 5 times x minus 1 all over x plus 5. And look what happens. My function simplifies down to just be x minus 1. So my function value is equal to x minus 1 at all points except at negative 5. Because remember, I cannot plug negative 5 in, but I don't have to worry about that at all because we're plugging in 3, not negative 5. So f of 3 is going to be equal to 3 minus 1, which gives me 2. So my point x0, y0 is 3 comma 2. So I'm going to write that I'm going to find the inverse function's derivative at my y0 value of 2, and that's going to be equal to 1 over f prime of x0, where x0 is 3. So I got to find the derivative at 3, which, if this is my new function value, as long as x does not equal negative 5, what's the derivative of x minus 1? That's simply 1. So my slope is 1 everywhere along the function except at that x equals negative 5 value. So I'm going to have 1 over 1, which equals 1. Now, if I would have asked to find the derivative at an x0 value of negative 5, we would not be able to find that inverse derivative because the original function is undefined at that point and not differentiable. Let's move on to our next section where we're going to be going over derivatives of trigonometric functions. Now, similar when we did derivatives of trig functions, I recommend memorizing these 6 basic derivatives. However, there are patterns between those which make memorizing easier. So let's work through each of these now. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. Similarly, the derivative of the inverse cosine of x is a negative 1 over the square root of 1 minus x squared. All right, moving right along to the inverse tangent function of x, that's going to be 1 over 1 plus x squared. That's that derivative. And the derivative of the inverse cotangent of x, similarly, is going to be negative 1 over 1 plus x squared. And then lastly, we'll do the inverse secant of x, that derivative, and the inverse cosecant of x, that derivative. So the derivative of the inverse secant of x is 1 over the absolute value of x times the square root of x squared minus 1, whereas the inverse cosecant of x is going to be the same thing, but the opposite. Just like up above, we have a negative 1 over the absolute value of x times the square root of x squared minus 1. So really, in all honesty, you only need to remember these first three and know that the inverse cosine, inverse cotangent, or inverse cosecant is the opposite of those others. Now, I also want to make a note that we have to remember the domain of our function. So right off the bat, a couple things we can't plug in for x, for the inverse sine of x and the inverse cosine of x, for those derivatives, we can't plug in a 1 or a negative 1 because that would give us an undefined answer because the denominator would be equal to 0. So the domain for the inverse sine and inverse cosine of x is going to be negative 1 is less than x, which is less than 1. That is our new domain. Let's discuss domain and range of tangent and cotangent. So we can plug negative infinity all the way up to infinity, values in between those for x. And then lastly, let's now look at the inverse secant and the inverse cosecant. So the domain in this case of our inverse functions, we are now going to have that x is less than negative 1, and we're also going to have that x is greater than a positive 1. So zooming out so you can see everything all together, each of the inverse trig functions derivatives and their domains. So now that you have those written down, let's do example 3, working through the derivatives of these inverse functions. For part A, we're taking the derivative with respect to x of the inverse sine of 4x. What are we going to do? Think about that chain rule. We're first going to take the derivative of the inverse sine of some function and multiply by the derivative of that function. So we know that the derivative of inverse sine of x was 1 over the square root of 1 minus x squared. But we don't have x, we have a 4x. So we're going to have 1 over the square root of 1 minus 4x squared, and then we multiply by that derivative of 4x, which is 4. So this becomes 4 over the square root of 1 minus 4x, that quantity squared. And again, what I did is I used my formula for the inverse sine of x, but I didn't have x, I had a 4x. So I plugged 4x in where I saw an x, but I had to also remember to multiply by that derivative of 4x, which is 4. Remembering that chain rule. Let's move on to part B. In part B, we're going to take the inverse cotangents of the square root of 3r plus 4 with respect to r. Just because I switched up the variable doesn't matter, we still take the derivative the same way. So the inverse cotangent of x, how do you take that derivative? That was negative 1 over 1 plus x squared. So I'm going to have a negative 1 over 1 plus the square root of 3r plus 4, that quantity squared, but then I still need to multiply by the derivative of my inside function, which is a chain rule in itself. That is 3r plus 4 raised to the 1/2. So I have to bring my exponent of 1/2 down in front and then I'll have 3r plus 4 raised to the negative 1/2, and then I still have to multiply by that derivative of the inside, which is 3. So let's go ahead and simplify this problem down. You can see here was that derivative pertaining to the inverse cotangent function, negative 1 over 1 plus x squared, but I didn't have an x, I had a square root of 3r plus 4, and then that was the derivative of my next function, and then finally my innermost function. So simplifying this down, we're going to get negative. In my numerator, it looks like I just have a 3, so I'll write negative 3 all over 1 plus the square root of 3r plus 4 squared becomes 3r plus 4, and that gets multiplied by writing this exponent as a positive in the denominator. That'll be 1 over 2 times root 3r plus 4. And then continuing to simplify down, I'm going to have a negative 3 all over 1 plus 4 plus 3r is going to be 3r plus 5. And that gets multiplied by 2, and also the square root of 3r plus 4. And that's my solution in part B. Feel free to distribute that 2 to the 3r plus 5 to get 6r plus 10. But that quantity needs to be multiplied by the square root of 3r plus 4 in that denominator. Let's move on to part C. In part C, I'm going to have to do a little bit of product rule because I have one function, e to the 6x cubed, times another function, the inverse sine of x. And for this sake, let's do a little bit of bookkeeping, practicing that skill. So my first function is e to the 6x cubed, and my second function, g of x, is going to be the inverse sine of x. So my derivative, f prime of x, using that chain rule is, well, e to some function, that derivative is e to the function times the derivative of the function. So e to the 6x cubed times, what's the derivative of 6x cubed? That's going to be 18x squared. And then my g prime of x, inverse sine of x, that was 1 over the square root of 1 minus x squared. Now, first times the derivative of the second plus second times the derivative of the first. So I'm going to have e to the 6x cubed all over the square root of 1 minus x squared plus, you can see that was my first times the derivative of the second, plus my second inverse sine of x, all multiplied by my derivative of my first, 18x squared e to the 6x cubed. And there we have it. That's my derivative in part C. Now moving on to the last example in this worksheet, we're going to be taking the derivative with respect to t. And again, it's going to be a little bit of product rule. First times the derivative of the second plus second times the derivative of the first. So I'm going to have first, which is the inverse cosine of t, times the derivative of the second. What's the derivative of inverse sine of t? That's going to be 1 over the square root of 1 minus t squared. And I'm going to add that to second, which is my inverse sine of t, times the derivative of my first. What's the derivative of the inverse cosine of t? That's a negative 1 over the square root of 1 minus t squared. So this is going to be equal to, I have a common term in each, that 1 over the square root of 1 minus t squared. So if I pull that out of each, I'll have 1 over the square root of 1 minus t squared, and that's going to be multiplied by the inverse cosine of t plus a negative inverse sine of t, because I only pulled out the positive 1 over square root. So I'm going to subtract the inverse sine of t. And if I want to, I can write this as one fraction. Inverse cosine of t minus inverse sine of t all over the square root of 1 minus t squared. And that's my final derivative on this worksheet. If you have any questions on how the inverse function works, please refer back to a previous example video where we talked about inverse functions. And if you have any questions on those inverse trig derivatives, please reach out and let me know. As always, I recommend doing some more practice problems, taking problems from your textbook or an online resource and going through them on your own. And once you practice, feel free to continue on to the next video. But until then, good luck with your online learning.